Hello, and thank you for joining us. I am here with Manuel Frick, and together we are excited to share how ARBURG, a manufacturer of injection molding and additive manufacturing equipment, quickly aligned their internal resources to design, prototype, and mass produce a medical-grade reusable face mask in just 41 days. My name is Jerry Barbarian, and I head up the ARBURG additive business here in the US. I have had the opportunity to spend over a decade in the additive industry, watching 3D printing expand from more or less an unknown prototyping method to a widely adopted solution for prototyping to low-volume production and everything in between. It's been an exciting ride, and I love seeing feel-good stories like this, where 3D printing was able to step up and aid a good cause.
My name is Manuel Frick. I am working for ARBURG since 2012. I have started as an application consulting for elastomers, specifically for liquid silicon rubber and multi-component molding. In 2016, I moved to Taiwan as a director of technology and application and to build up the LSR market for ARBURG in Asia. Last year in July, I came back, acting now as a sales manager for liquid silicon rubber worldwide. Now we could ask the question, why did ARBURG decide to get involved? The PPE was short in supply, current manufacturers could not keep up, and that put lives at risk. With the tools at hand and the production ability, we felt it was our civic duty to get involved and help. The products are delivered free of charge to local distributors and hospitals. This was the most important point for us. How did the project start? The initial idea of where to get involved came from a call of an employee of the hospital in Rottweil. The hospital was going to run out of personal protective equipment. She remembered us producing sunglasses at the K-Show in Düsseldorf last year. She asked if these sunglasses could be produced transparently and be used as protective glasses. ARBURG quickly set up a system devoted to producing the glasses and kicked off a production run. Luckily, the mold from UVEX was still available and our partner EMS Chemie had quick access to the correct material. We were able to go from request to production in only 25 days. ARBURG took pride in the ability to offer assistance to surrounding hospitals and delivered all of the supplies at no costs. Simultaneously, one of the managing directors at ARBURG Germany had an idea. He was concerned about the availability of the masks for his employees in the midst of the crisis. As I'm sure you all remember, most PPE, like gloves, masks, face shields, normally available to anyone, was diverted to healthcare organizations. So he turned to ARBURG's additive group to design and print masks for first tests.
The first mask concept was to cover and divert. The design essentially covered the face and directed exhaled air down and away, thus protecting the user from any aerosol particles coming towards them and protecting others from any aerosol particles exhaled by the user. The user's breath would be directed down and to the sides, thus being trapped in their clothing. It was a simple and seemingly effective concept. ARBURG's additive group had the tools to quickly turn a concept into a prototype and even do some low-volume production work. The group's main tool is the Freeformer, a 3D printer. It enables quick prototyping of different variants of the mask. They're able to do some versions in a single material model and others in a dual material model. The Freeformer comes in two models. Our 200 on the left is our two-nozzle system, capable of printing two materials or one material plus a support material. The 300, our larger system, is a three-nozzle unit capable of printing three materials or two materials plus a support material. It's also available with a high-temperature package for those high-temp material needs. What makes the Freeformer an ideal tool for prototyping face masks is the ability to run any granulate material through the system once it's been tuned for it. The material is loaded into the hopper on the top right, then processed through a screw and barrel, And lastly, extruded through a nozzle as a string of micro droplets. This processing method allows the user to control the system and print parts in varying densities, from fully dense and similar to a molded part, to a very low density, creating a lightweight part. With this material flexibility, the team could use medical grade materials, either rigid or flexible, to print face masks that could be used without any danger to the user. No post-processing or coating of the parts is needed. The first mask concept was designed and printed on March 26th, just a few days before the glasses project kicked off. The first design was printed on the freeformer in a flexible Shore 70A TPU, or thermoplastic polyurethane. The material used was a medical grade material and safe for the user to put directly on their face. The quick turnaround of this concept from a request to a part in hand was an immediate success internally. So much so that it pushed those involved to wonder if they could do more. What's stopping ARBURG from designing and producing a fully functional PPE mask using the resources available? We have the ability to prototype any design with the freeformer and the resources to move into mass production with our molding systems. The bottom line, nothing is stopping us from stepping up and helping with the PPE shortage. To start our mask design, we looked at all of the available masks on the market. What are the pros and cons of each one of them? First, we looked at the disposable mask. It's inexpensive, but it also doesn't last very long, and it's not very good for the environment since it creates waste. We then looked at the fabric mask. It's better for the environment, and it's relatively inexpensive, generally between about $10 and $20 a piece. There's tons of versions and sizes available though, so it's tough to know what the right version for you is. And you're going to need multiple since they have to be washed between each use. That's the route my wife and I took, and we probably have about $100 invested in masks sitting in a bowl by the door. The next one we looked at was the full face mask. This is overkill for the general public. Even if you wanted one, you can't find one. They're all reserved for medical workers. Last, we looked at the common half respirator. This is a good design with a replaceable filter. However, they're expensive and generally unavailable. How can we take this common half respirator design and make it better and make it available? Before we get to our design, we are curious what those of you listening prefer to wear. In the chat area, let us know what type you prefer. Type 1 for a disposable mask, 2 for a fabric mask, 3 for a full face mask if you've had access to one, and 4 for a common half respirator mask. We'll wait a few seconds to see which mask is the most popular. With a general idea of the type of mask we wanted to create, we started by laying out some goals for our design. We immediately took price off the table as we intend to donate these. Flexibility is important. Could one size fit all, or maybe we need 2 sizes? It needs to be simple to decide which size is right for you. The mask needs to be sterilizable. We do not want to create more waste. It would be best if we can sterilize it with either alcohol wipes or hospital-grade sterilization. We want to standardize it. We want our mask to be compatible with filters or respirators. We'll aim to use a standard connection to make the mask flexible for whatever the user needs. Lastly, we want to be able to function with no filters, mimicking the original concept. At ARBURG, we are machine designers and manufacturers. So we leaned on the molding machine designers to design a mask that fit the criteria we laid out. The designers split the mask into 3 separate parts, each with their own function. A soft and flexible piece that would be in contact with the user's face. We called this the LSR mask. A rigid piece that would hold the mask to your face and act as a support structure for the flexible piece. We called this the Smart Shield. And a filter and exhaust valve that would do exactly what their names suggest. filter the incoming air, and exhaust the outgoing air. Once the basic design was created, the design team passed the torch to the additive team to create and test the prototypes. The additive team looked at the design criteria passed down from the machine designers. People have different size faces. Myself at 6'4" would likely have a different size face than a person who is 5'5". Do we need different size masks? What about male versus female? They have different proportioned features. Do we need different masks for males and females? The mask needs to be strong enough to retain its shape, but soft enough against the face so that it's comfortable for long periods of time. Can that be one semi-soft material, or does it need to be two materials, an ultra-soft combined with a stiffer material? Liquid silicone rubber was the ideal material for the final mask. It's a common medical material used with face masks. It's durable at high temperatures and easy to sterilize with hospital-grade sterilization or alcohol wipes. Neither will cause the silicone to degrade. Plus, it's soft and molds nicely to the face, ensuring there are no air gaps. With some ideas in mind, the additive team started printing different versions of the LSR mask. They printed several sizes and shapes and passed them around for people to try on. Male and female employees tested different sizes, and the outcome was that one medium version fit everyone. When comparing a single material version against a multi-material version, some questions arose. Will the filter sag and flop around with a single soft material version? The team printed versions in a medical grade Shore 30 TPE and then in a combination of a PCABS and a Shore 30 TPE. The single material version felt the best and worked nicely when combined with the Smart Shield. Lastly, the team printed several varying softnesses to decide on the final material's Shore value and what felt best on the face. The Smart Shield is the frame of the mask. It will wrap around and hold the LSR mask and attach to the filter. It needs to be rigid enough to hold the mask securely to the user's face and to securely connect the filter. However, it needs to be flexible enough to bend around the mask and not break when removing the entire apparatus. Lastly, there will be a cover to snap over the filter connection and allow the mask to still be used without a filter by directing the exhaled air downwards. The additive team looked at the design criteria for the Smart Shield and chose to prototype it polypropylene. Polypropylene was the ideal material to test the snap fits and the living hinge on the cover. The team was able to make small adjustments in the snaps and the hinge to assure the longevity of the device. The material also gave the part enough flexibility to wrap around the mask and not break when removing the LSR portion. The polypropylene material worked so well for the prototypes, it was decided that it would be the final production material as well. The mask was designed to be used with commonly available filters from suppliers such as 3M or Honeywell. But during the height of the crisis, these filters were not available. So ARBURG needed to design and produce their own. The filter and exhaust valve design were quite straightforward. Standard connections, built-in air valve, built-in exhaust valve. The shape and size were the biggest question. The team started with a generic round design, as you can see in the top picture. Once the part was printed and assembled, it was quickly clear that the filter was too large. When wearing the mask and looking forward, it limited visibility. So naturally, they scaled the size down and reprinted. The new version was assembled and fitted to the mask. The visibility problem was solved, but this created a new problem. There was not enough area for air to be drawn in over the filter. The design noticeably limited the amount of air a user could draw in and caused a shortness of breath. There had to be a better solution. What about a larger filter, but with a different shape? A few concepts were drawn up, quickly printed out, and tested. The final winner was a triangle-shaped version. The new triangle shape was just as large as the first design, but the contouring of the top edges solved the visibility issues created by the first filter design. The group used PCABS for these prototypes. The material was chosen because it performed well with thin walls for the filter design and the snap on the cover. It was also a medical grade of PCABS, so it gave the production team a head start on material choice. Finally, the exhaust valve, the heart of the filter. It was a simple design, but material was in question. The group chose the same PCABS for the filter exhaust valve. This allowed the fabric filter to be sonically welded to the valve. Being able to test the sonic welding prior to production and proving out that assembly process gave the production group a head start.
So far, you have heard a lot about the details of the design and the technical specification of the mask. Now I want to take a closer look into the industrial production. As already mentioned at the beginning of the presentation, the initial start was in the end of March. After finishing the design of the LSR part, we had to do various simulations to ensure a perfect quality in such short term of time. Due to the low viscosity of LSR during the injection process, the risk of a trapped air bubble is quite high. This can be avoided with the correct part design, gating points, and the correct mold setup. All those details can be foreseen with a good simulation software. Parallelly, we had to start with prototypes of the mask and the filters to test them with various phase counters. Our target was to have one design which can fit on different faces, like for females, males, with glasses or without glasses. This is the full overview of the milestones of the project. From the really start to the fully automated production, we had only 5 weeks, which is really a masterpiece. Due to the fact that LSR molds have to be super precise, we were still able to overcome this in the short of the time. A great help was the in-house additive manufacturing team supporting us all the way long. With the prototypes in the very early stage of the project, a lot of surprises were avoided. Coming now to one of the most important topics for such big projects: a really good network. Only with a good interaction of many companies, this mask was able to be produced within 41 days. Starting with the simulations, further to the right choice of the materials, up to the precise work of the mold makers, everybody was working with the highest motivation to do something unique in this difficult situation. All in all, 14 companies were involved in this project. Last but not least, an impression of the production cell itself. The machine in the background was running the protective glasses with the mold from UVEX and the material from EMS Chemie. It was a single cavity mold with a cycle time of approximately 45 seconds. With this setup, we were able to produce almost 2,000 glasses every single day. The machine in the foreground was running the LSR mask production. It was a 4-cavity mold with a cycle time of 50 seconds. An output of roughly 6,500 pieces each day could be achieved. On the right-hand side, you can see the masks in the gripper of the robot cooling down for further process steps. All in all, the footprint of the cell was optimized to fit into the corner of our brand new training center. Thanks to the colleagues, the machines were set up in a couple of hours to start the production as fast as possible.
There are a few lessons that I hope stood out during our story. Number 1, get involved. If you have the resources to help during a crisis, please do. Those in need will be ever grateful. Number 2, all hands on deck. At ARBURG, everyone stepped up to play their part and make this vision a reality. Don't let corporate structures stand in the way of making great things happen. And number 3, amazing things can be done with the right tools. From concept to production in 41 days. This is a fast design cycle. but it's possible with the correct tools. Let the lessons we learned make your organization successful too. Bring flexibility to your prototyping. Use the correct materials when prototyping. Don't sacrifice. Use a prototype to test not only your fit and form, but your function too. Test your manufacturing process during your prototyping phase. And above all, don't limit what a functional prototype can do for your organization. Thank you for joining us, and we hope you enjoyed our story. If you have any questions about the mask design and production, or want to explore a different application that's important to you, please join us at our booth. We will be available the rest of the show. Thanks.